Good afternoon and welcome to the 21st annual exhibit of hydrogen and fuel cell technologies. We've been discussing this technology for quite some time. There's always innovations, there's always new things happening, and there are research facilities in Germany that really are the best in the world. One of them, everyone knows what it is, Fraunhofer. Those people who use MP3s have been informed about this institution for decades now. They also specialize in energy technologies. They're forerunners. And we have someone to inform us about current developments. It is Dr. Markus Tegel, who's project manager of Hydrolysis, a hugely important topic at the energy, for the energy budget. He's from the Fraunhofer-Institute for Manufacturing Technology and Advanced Materials. And he'll be discussing PowerPaste, high dynamic and safe hydrogen on-demand solution for fuel cell applications. Please welcome with me Dr. Markus Tegel.
Thank you very much for that really kind introduction. My talk today will be about PowerPaste, as you heard. In this picture, you can see PowerPaste. It is an ultra-high energy containing material, as you will see. And we can produce electricity, but first hydrogen from it. How it works, you will see in a couple of slides. For the invention, we've been awarded with the 2013 EFSAL award, and we've been also very recently featured on television in the Inventors magazine Einfach Genial, which you can still see online at the media center. Probably everybody of you knows the limitations of batteries. Batteries are excellent, but they have limits regarding their capacity, their durability, so batteries only last usually a couple of years before they degrade. They have self-discharge. They are quite heavy weight and quite large sizes if you want to store significant amounts of energies. You're dependent on the electricity grid to recharge them, and then you need several hours usually of recharging time to fully charge them. And you're also limited temperature-wise. So for example, during cold winters, for outdoor applications, usual batteries are just not suitable. We at Fraunhofer IFAM propose a solution to these problems, a hydrogen-based energy on-demand system. How this energy on-demand system works, I want to show you in this picture. The magic behind it, the end user just needs two components. One is PowerPaste, and the other component is water. If you insert this into our system produces hydrogen on demand, and then a fuel cell in our system converts the hydrogen to electricity. We think there are many applications for these kind of electricity and power storage systems. First of all, we think of applications as stationary systems, for example, for backup power solutions. As many of you know, fuel cells are already around and being used for backup power systems, but you've always got the problem with the hydrogen infrastructure there, and certain applications you just cannot do with gas cylinders. We also think of disaster recovery applications, or for example, surveillance applications like CCTV. But on the long term, our systems could also be used for portable and also mobile systems even. Basically for portable and mobile systems, because you have extremely high energy densities, it's easy to use, you've got no noise and zero emissions, And for the stationary systems, you're completely independent from an energy grid, and you've got high reliability as well as low OPEX costs. So how does the technology work? In the PowerPaste, there's magnesium hydride. That's a hugely energy-containing material, and if you mix the PowerPaste with water, hydrogen is produced. And one special thing about this reaction is that half of the produced hydrogen actually comes from the water, the other half comes from the magnesium hydride. So that really doubles the amount of hydrogen which is inside the magnesium hydride in the PowerPaste. Then the hydrogen is converted to electricity. To give you numbers, the energy inside the PowerPaste, just the amount of hydrogen which comes out is 3.2 kilowatt hours per 1 kilogram paste. And after conversion in a fuel cell, you still have 1.6 kilowatt hours per kilogram, which is enormous. Why haven't you heard maybe about PowerPaste so far? Well, basically, it's not that simple. If you use normal magnesium hydride and want to react it with water, you will see nothing or next to nothing happens. Only a very slow reaction takes place. In this chart you can see the hydrolysis time over the reaction progress. And what you can see here in this curve, normal magnesium hydride just doesn't react at room temperature with water. That's because magnesium hydroxide passivation layers form on top of the magnesium hydride, which prevent any further reaction. We found a suitable, cheap additive to improve the reaction, and then we've taken even one step further and invented PowerPaste, which is really highly dynamically reacting with water. Another peculiarity about PowerPaste is that it will react with any kind of water. So you can just use normal tap water, but also seawater, deionized water, of course, but you could even think of wastewaters. We filed several patents, which are still pending for PowerPaste, and also very recently submitted a paper in the Journal of Power Sources. Another special thing about PowerPaste is that the release of hydrogen is exactly dosable. So the reaction behind it is completely controllable. And we do this by a microcontroller control unit, and it is able to produce the hydrogen just as it is needed by the fuel cell. And we do this with simple components, a paste dosing system, and a simple water pump. To show you PowerPaste in action, how it really produces hydrogen, I've prepared you a short video. Here you can see a so-called hydrolysis setup, so where PowerPaste is reacted with water. That's the microprocessor control unit. And here inside this simple reaction vessel, PowerPaste is just being mixed with water. Here you can see how the reaction takes place. 50 grams PowerPaste per hour are consumed in this video. And here you can see how smoothly the hydrogen is produced. We're talking about 1 norm liter per minute, which is the equivalent of 160 watts of chemical energy or 80 watts of electricity in this very, very simple reaction. So, what are the advantages of PowerPaste? I think it's best to compare it with other technologies. Compared to rechargeable batteries, you have 10 times more energy per volume and weight. You have no self-discharge. You're completely independent from the electricity grid. PowerPaste also works in cold climates, as low as minus 30 centigrades. And you have an immediate refill. You can just replace a PowerPaste PowerPaste cartridge with a new one. Compared to methanol-based systems, you have power immediately by the fuel cell. You can build lighter systems as the fuel cells are much lighter. PowerPaste is non-toxic. You can use cheap PEM fuel cells, so you don't need high catalyst loads. And it's easily scalable from the watt scale to the tens of kilowatts scale. Compared to normal gasoline or diesel-based power generators, you've got no noise, no emissions. You can use it indoor. You have low maintenance costs, which is especially important for backup power applications, and you have a green energy solution. On this chart, I have a comparison of energy densities of several energy-containing technologies and materials. For example, once again, the lithium-ion batteries, special batteries, methanol, gasoline, and PowerPaste. If you include efficiency losses, so to convert the energy of these materials to electricity, which I have done here, PowerPaste has the highest energy density of all of these materials, so 10 times more than batteries. We haven't stopped there. We've built and constructed within the last year a whole system, a TRL4 prototype system, which runs on PowerPaste, which doesn't only produce hydrogen. As you can see, the hydrogen is really evenly produced. It is also able to convert this hydrogen to electricity, so it is combined with a fuel cell already. If you're interested in this technology, I'm looking forward to your questions, or you could visit us at our booth, which is just next to the technical forum. Thank you very much.
Thank you. I'm sure we have some questions from the audience. Yes.
So the question is, what's the state of affair right now? So how soon would this be available, for example, on the market?
So we are going to commercialize this technology within 2 years from now for the first application. Currently, we are sure backup power is the first application for this, but this could be later on used for mobile applications. So we're going to run a startup in 2 years' time from now.
Other questions? Yes.
Yeah, hello, I have a question. Is this material rechargeable? So can you store the hydrogen without any major additions again in the magnesium hydride?
So basically, it is like a primary battery. So it's a single-use reaction, but of course, you can recycle the material, or as we propose in an earlier stage, you can downcycle the material to magnesia, which is especially important for the stationary applications. Magnesia is widely used in the industry, and we found an easy solution for this. And later on, you can think of full recycling. And also, what is really important for the small applications is that you can simply dispose it. The only byproduct, magnesium hydroxide, is also non-toxic, so you can dispose it in a normal waste as well.
Do I see any other questions? No one's asking you the tough questions, so I'll have to grill you for a while here. Question number one would be, magnesium's not cheap.
Yes.
So this isn't going to fly unless you can recycle the magnesium. So where do you stand on that issue?
I think magnesium is not too expensive. We are talking about a magnesium price of around €2 per kilogram. It slightly changes from time to time, but that's the average price. If you convert this to electricity, you have an electricity price of, in a perspective, on the long run, €1.20 per kilowatt hour, which is perfect for backup power solutions, because it doesn't depend how much backup power costs as long as the system runs. So the system rarely runs, so it doesn't use that amount of PowerPaste, that large amount.
I mentioned this because there was another presentation. The alternative is magnesium hydride,
Yes.
which exists in the form of a solid. This will pertain to your dosage system here because the magnesium hydride is literally a cube. You can drop into a water source, cap it, and it slowly releases, which could be a benefit in certain cases. Fast release, of course, for energy density is kind of an interesting thing. Slow release is fine, but if you want to get more power, you open up again and drop in another cube. For some applications, it's fine. Specifically, so for your application, you literally continue the flow of paste into a receptacle where it reacts with water. That's how it would operate.
Correctly. That's correct. I think for every power on demand or hydrogen on demand system, it's important to control the reaction. So fuel cells have changing loads, and you can exactly match changing loads by changing the dosage of PowerPaste and water. And that's what you cannot do with solid liquid systems like normal magnesium hydride.
Okay. Whenever we talk about a source for hydrogen, we all know there's various fuel cell technologies. The higher temperature solid oxide fuel cell systems are incredibly generous. They don't give a damn what you put into them. You know, literally, it's fantastic.
Yes.
Seriously, it's wonderful. I mean, the applications are manifold because you can use the same technology and run it on natural gas. You can run it on oil, diesel. You can pour your whiskey in there, take your wife's perfume if it doesn't smell right, dump it in. You're fine. You mentioned that you could use your paste with contaminated water as well. It doesn't matter. Do you still get pure hydrogen out of the system? This is vital because PEM cells hate the least bit of impurity does damage to very expensive platinum technology. So how pure is the hydrogen that comes out of your system?
So we've run actually several tests on this, and what I can say with normal water, tap water, as well as deionized water, it's perfectly fine. You have a hydrogen purity apart from water vapor, which exceeds 4.0, which is fine for PEM fuel cells. Also, the traces of contaminants are not critical for the fuel cell. If you're talking about wastewater, of course, this would depend on the wastewater. There could be several compounds which might be an issue. We don't know that yet. We haven't tested that yet. But still, as for example, the whole reaction system is an alkaline suspension. For example, carbon dioxide is no issue because it will dissolve in the water and it will be there as carbonate, for example. So many contaminants can be ruled out.
Okay, I see the energy density advantage there. I'm still wondering about the magnesium recycling issue. Our colleagues at Tohoku University from Japan have advanced that issue. It would be an interesting cooperation there because they actually allow the recovery of magnesium hydride, the recovery of magnesium. That is their key, and it's quite an advancement. So it'd be interesting to see how that dialogue would continue. But on the issue of energy density here, you still mentioned stationary applications as the first application.
Yes.
We are faced with an issue that is non-solvable unless you do something with hydrogen. Hydrogen has a lousy energy density. So if you want to drive a car 500 kilometers, you really have to go for a 700 bar tank. That itself takes energy, and it's still not the energy density that people expect from an automobile. So in terms of mobile applications, can you envision installing a system like this? Do you get to, we're talking about footprint and not simply weight. If you take the typical gas tank size of a conventional automobile, would you be able to do 700 kilometers? Very efficient cars manage that.
You could do this with the technology, I'm sure about this. It's a question of the price rather than of the feasibility. So basically you have 10% hydrogen stored inside that material, so that exceeds all DOE targets. So that would be highly suitable for mobile applications.
And of course it's not dangerous if the idiot behind you crashes into you.
Exactly. So what is especially important is you have nearly nil pressure, so you can directly match the input pressure of any fuel cell.
Okay. Well, it's obvious that we have to continue this. Oh, we have one question here. We only have a minute left, but
You said it is a green energy. Well, if you dispose the magnesium, it's critical, I think. And on the other hand, you said you assume a 50%
Efficiency.
efficiency. Thank you. How is about the system efficiency if you've got to produce the PowerPaste?
Yes, I've also run several calculations on this. So if you're talking about a full recycling concept, really power to power, which is always tough and efficiencies are always low, an honest efficiency is around 20%, which is still fair enough considering that you really can store really high amounts of energy.
I see that though as a critical issue, and this is why the dialogue is so important. Recovering the magnesium would make this a win-win technology, particularly facing the energy density issue. So we'll have to continue that dialogue. We've run out of time though. I've been talking to Dr. Markus Tegel, who's project manager of hydrolysis at the Fraunhofer-Institute. It's been a pleasure. Hope to see you back next year.
Thank you very much. It was a pleasure.
Thank you. We'll be continuing in 45 seconds with our next conversation.